Hi, this is Sonia Doucette, and for this video I'm going to show you how to calculate the equilibrium concentrations of various products and reactants when you know Kc and you also know the initial reactant concentrations, not the equilibrium reactant concentrations, but the initial reactant concentrations. So we're starting out with reactants present at some concentration, but no products present yet. So the problem that we're going to do is this one. Calculate the equilibrium concentrations for the reaction Fe2O3 plus 3 carbon monoxides gives you 2 irons plus 3 carbon dioxides. And you know that Kc is 19.9 and that the initial concentration of carbon monoxide, which is one of the reactants, is 0.200 molar. So what you're going to do for these problems is set up what's known as an ICE table. So ICE tables help you when you have a problem where there's more than one unknown to solve for. So in this case, we want to know the equilibrium concentrations of all the reactants and all the products. So therefore, there's more than one unknown. So the I, the C, and the E in an ICE table all stand for something. So I refers to the initial concentrations of products and reactants. C refers to the change in the concentrations of the products and reactants, and specifically how those concentrations change in order for the reaction to reach equilibrium. And then finally the E, as you may guess, is the equilibrium concentrations for the products and the reactants. So what you do to start is you write your balanced equation at the head of the ICE table. This is standard practice for any type of ICE table problem. So I'm going to rewrite our balanced equation here. Oops. Okay, and then at the head of your table you have your balanced equation, and then you're going to have 3 different rows. One row will be named initial, and this will be your initial concentrations. The second row will be change, and this will be the change that your initial concentrations will experience in order to reach equilibrium. And then the last row will be your equilibrium concentrations. So you're given Kc for this problem because what you're ultimately going to do is use that Kc value, which in this case is 19.9, to help you solve for the equilibrium concentrations of the products and reactants. So one of the first things you want to do then is after you write your ICE table, is to write your equilibrium equation. So in this case, equilibrium equation is going to be Kc is equal to products over reactants. So if you'll notice for your products, you have iron as a solid and carbon dioxide as a gas. So remember that when we're writing equilibrium equations, we're going to include certain things and omit certain things. So one component that's omitted is a pure solid. So iron is a pure solid as a product. So therefore, it's not going to be included in the equilibrium equation. So the only product that you'll include here is the concentration of carbon dioxide gas. And that will be raised to the 3rd power because carbon dioxide gas has the stoichiometric coefficient of 3 in the balanced equation. So that's the only product you'll include. So product over reactants. And again, Fe2O3 solid is a pure solid. So that will also not be included in the equilibrium equation. So the only reactant that you'll include here is carbon monoxide gas, also raised to the 3rd power because it also has the stoichiometric coefficient of 3 in the balanced equation. So now you understand which components you're dealing with here. So when you think about the initial concentrations, you can negate or neglect Fe2O3 as a pure solid. You're given the initial concentration of carbon monoxide gas. So in the row for initial, under carbon monoxide gas, you're going to write 0.200. And as I already mentioned, in these problems, you know initial concentrations of reactants, but there are not yet any products present. So in terms of CO2 gas, you can write 0 for initial concentrations because none of the product has been formed yet. And similarly to Fe2O3, because iron is a solid, you also won't pay attention to the concentrations of iron. So you're only dealing with the concentrations of carbon monoxide gas as the reactant and carbon dioxide gas as the product. So the next thing you need to do is move down to the next row that says change. And what you're going to do is define X as the concentration of carbon monoxide gas that reacts in order to reach equilibrium. So one thing you need to do here is realize that this will be negative because you're going to be losing carbon monoxide gas as it reacts with the Fe2O3 to give you products and to reach equilibrium. And the other thing you need to do is you need to include the coefficient from the balanced equation in your change. So because carbon monoxide gas has a stoichiometric coefficient of 3, you need to include that 3 for the change. So overall, the change for carbon monoxide gas will be minus 3x. And on the other side, for every 3 moles of carbon monoxide gas that react, you get 3 moles of carbon dioxide gas as product. So what you're going to do is add 3x to the right-hand side of the equation in the change row. And then finally, all you need to do is add or subtract the initial from the change to give you your equilibrium concentration. So for carbon monoxide gas, that's going to be 0.200 minus 3x. There's your equilibrium concentration for carbon monoxide gas. And then for carbon dioxide, your equilibrium concentration is 3x. So you still don't have a number or a value for those equilibrium concentrations, but you have stated them in terms of x, which is your unknown. So the next thing you can do is substitute all of the things that you know into your Kc expression or your equilibrium equation. So what you're going to do here is say 19.9, because that's your Kc value, is equal to 3x cubed, because 3x is equal to your carbon dioxide concentration in terms of x, and this is your numerator for the Kc expression. And then in your denominator, you're going to put the carbon monoxide gas. So in terms of x at equilibrium, you know that that's equal to 0.200 minus 3x. And you also need to raise that to the third power. So then you need to solve for x. And once you solve for x, you can substitute x back into your equilibrium concentrations and get actual numbers for your equilibrium concentrations. So to solve for x, the easiest thing to start out is to take the cubed root of both sides, so you can get rid of those 3's for both the numerator and the denominator. So when you do that, you'll get 2.7099 is equal to 3x over 0.200 minus 3x. So you've gotten rid of those cubed terms, which is good. That'll make it easier to solve for x. The next thing you want to do is solve for x and continue along here. So you're going to multiply both sides by 0.200 minus 3x. And when you do that, you'll be left with the following. So you have 2.7099 times 0.200 minus 3x is going to be equal to 3x. So you multiply out of the parentheses to get 0.54198 minus 8.12966. X is equal to 3x. And then you move this term to the other side of the equation to get the x's on the same side. So 0.54198 is equal to 3x plus 8.12966x. So you're almost there. So you add your x terms together on the right hand side there to give you 11.12966x, and then you multiply both sides by 1 over 11.12966 to get x by itself. And what you'll be left with is x is equal to 4.86966 times 10 to the negative 2. So now you know what your x is, and you can substitute this x back into the equilibrium concentrations for carbon monoxide gas and carbon dioxide gas expressed in terms of x. So to solve for the concentration of carbon monoxide gas at equilibrium, you know that that concentration in terms of x is equal to 0.200 minus 3x. And now that you know x, you can just substitute that number into this expression, and then you get your concentration of carbon monoxide gas at equilibrium. So this is one of the things that you wanted to solve for, 0.0539 moles or molar. You do the same thing for carbon dioxide at equilibrium, and you know that that's equal to 3x. If you look back up at your ICE table, you can see that. And all you have to do here is substitute in the x value that you just solved for to give you the answer here, which when you do the math will be 0.146 molar. So that's your solution. And it's a good idea to check your work. So what you can do here is substitute these values that you found back into the Kc expression to check and make sure you get the same Kc that you started with. So to check your work, you're just going to see that Kc is equal to the concentration of carbon dioxide gas cubed over the concentration of carbon monoxide gas cubed. You're going to substitute in those values you just solved for. So carbon dioxide gas is 0.146 molar cubed. Carbon monoxide gas is 0.0539 molar cubed. And when you solve, you're going to get 19.9 rounded to 3 significant figures, and that is your original Kc value. So you've checked your work, and your work was correct, so you're done.